Hi there, supermassive maths fans. Almond Bread joining in on the black hole fuss. I know I'm late to the party, but I hope interestingness does not decay over time. I want to share with you some confusion that spins around black holes for me. As a disclaimer, I'm an engineer, not a physicist, and my education about black holes comes from Hawking's popular scientific books that I vaguely remember and from the Wikipedia article about black holes. So, at my first contact with a black hole, figuratively speaking, I was confronted with the following concept. Every celestial body has an escape velocity. If you stand on the surface of a planet and you throw a stone away from it, three things can happen. First, you throw it up and it falls back down. It lands slightly next to you because this is a serious thought experiment and not slapstick. That's what happens when the velocity that you throw it up with is smaller than the escape velocity of the planet on its surface. Second, you throw it up much faster and it easily escapes the planet's gravitational field, forever flying away from the planet. This is what happens when you throw it faster than the escape velocity. Third, if you just throw it just right with exact escape velocity, it barely manages to escape the gravitational field, coming to an exact stop infinitely far away after infinite time. Any slower and it would have turned around at some point. Now it is said that on a black hole the escape velocity is larger than the speed of light. And nothing can go faster than the speed of light, so nothing can escape from a black hole. I had two problems with that. First, what if I'm not trying to escape a black hole on a stone or on a cannonball, but in an able to accelerate rocket? Provided that I have enough thrust for long enough time, I should be able to escape anything, no? Second, the fact that something is catapulted off the surface with a velocity lower than the escape velocity doesn't mean it won't go up at all. It only means it won't go infinitely far away, but return eventually, provided that nothing influences it on its way. So I should even be able to escape a black hole on a stone that is thrown up and then hit by an asteroid at some altitude. So I was convinced that I have just disproven black holes and all those physicists just don't have a clue about stuff. I was also excusingly young. By now I know that there is more to black holes than meets the eye, not. But I still stand by my reasoning, and I also still think that nothing can escape a black hole because they have an escape velocity faster than the speed of light is a sucky explanation. I also still like conceiving thought experiments that hair-raisingly oversimplify general relativity and approach everything from a Newtonian engineer mind, trying to squeeze the symptoms of relativistic effects into that framework without any deeper understanding. And this is exactly what we will do now, and it's gonna be fun. We will devise a hypothetical planet that shall carry the awkward name Lupa. And it will have rings. Any planet with any self-respect has rings. It is a very special planet. It is a sphere with Earth-like gravity on its surface and an event horizon slightly above the surface. And rings. The event horizon is also called Schwarzschild radius, which is coincidentally very fitting. Schwarzschild is German for black shield, but the Schwarzschild radius is named after its discoverer Karl Schwarzschild, who came from a Jewish family of traders of textiles who had nothing to do with black holes. Yeah, I know the black chalk was not my brightest invention, but you should see the guy. Anyway, at the Schwarzschild radius, the escape velocity is exactly the speed of light. But as discussed earlier, that's not why nothing can escape. Or maybe it somehow is, but then in a way that has nothing to do with throwing stones. Or maybe even that, but then not in a way that makes sense to me. However, let's do the maths. The gravitational acceleration acting on a point around a spherical object is determined by g equals gm over r squared, where capital G is the universal gravitational constant, capital M is the planet's mass, and minuscule r is the point's distance from the mass's center. The equation for the Schwarzschild radius is Rs equals 2gm over c squared, where c is the speed of light. Every mass has a Schwarzschild radius, but it's usually way smaller than the object having the mass, so other objects cannot enter it and be doomed. The mass of your mom, for instance, has a Schwarzschild radius of just around 0.2 yoctometers. With these two equations, we can determine the mass and the surface radius of Lupa to fulfill the aforementioned conditions. So let's say we want a gravitational acceleration of about 9.8 meters per square second on the surface, and we want the Schwarzschild radius to be around 2 meters above the surface, so we can comfortably stand in between. So we have the equations gravity equals gm over r squared, Schwarzschild radius equals 2gm over c squared, And the Schwarzschild radius is also the outer planet radius plus our 2 meters. Solving for r and m, we get r being around half a light year and m around 3 times 10 to the 42 kilogram. When I turned to Wolfram alpha to get an idea of how massive that mass is, it said it's about half the mass of the Milky Way. Oh, and 200 times the upper limit of the mass of a black hole. Whoops, so there is such a thing? But some quick reading suggests that this limit is only practical, not theoretical. We don't care about that in thought experiment land. Well, let's see how dense our planet needs to be. Density equals volume over mass equals sphere thing, and we get about 7.6 times 10 to the minus 6 kilogram per cubic meter. That is very undense. Wolfram alpha says that this is as undense as 0.57 times the density of Earth's atmosphere in 82 kilometers altitude. But we don't want Lupa to be as undense as 0.57 times the density of Earth's atmosphere at 82 kilometers altitude. We want to stand on it. But the thing is, that's just the average density we need, so we can achieve that by using any material and making the planet hollow like our Earth. And because we are very progressive people, we don't use concrete for that. Concrete production generates loads of CO2, and for the amount that we need, that would just be incredibly irresponsible. On the Flash Forward podcast, I heard about a green alternative, Farrock. It's made from iron dust and silica, and it actually binds CO2. And it will give our planet a vintage rusty finish that nobody can see through the event horizon, but we will know it's there. I couldn't find the density of Farrock anywhere, so I contacted its inventor David Stone, and it turns out it's around the density of concrete. We'll go with 2,800 kilogram per cubic meter. So the equation for the mass of our hollow sphere is m equals sphere shell volume times density, surprise. Solving for the inner radius, we obtain 4.6 godzillion meters, which leaves us with a wall thickness of about 4.2 thousand kilometers, ballpark Mars radius. So the blueprint of our planet is done. I know you can't wait to explore all the relativistic implications of our sick creation, but we're not there yet. We have to cover 2 more topics along the way that are as important as they are interesting: error analysis and statics. Error analysis is important because we care about the sums of numbers that are orders of magnitudes apart. So we need to know the larger part with the same absolute precision as the small part. As an example, you want to determine the thickness of a coin. You measure the distance between the upper side of the coin and the surface of the planet Pluto, and you measure the distance between the lower side of the coin and the surface of Pluto. You just subtract both measurements and you're done. Except if you only determine the Pluto distance thing to within a kilometer of precision, which would be terribly precise, you'd also determine the thickness of your coin to within a kilometer precision. In our case, we have around half a light year of planet radius and half a light year plus 2 meters of Schwarzschild radius. Assuming that we know all involved numbers to the required level of precision, which we do absolutely not, we can determine how precise we have to be with our planet measurements. Fixing the inner radius, we can determine the required precision of the outer radius given the target precision of the Schwarzschild radius, let's say 2 centimeters. We do some derivative action and some linearization, which never hurts. So radius variation is all this derivative stuff times Schwarzschild radius variation, which yields about 18 picometers, a bit smaller than the radius of a hydrogen atom. So although I already went nuts with the precision, that was still by far not precise enough. But that's just on average over a huge area, so in order to cope with this, we can just go the control theory way and keep adding material here and there until our Schwarzschild radius is exactly where we want it to be. So let's get to the second issue, the statics. Does Farrock actually withstand the pressure? Full disclosure, I have no idea how to calculate that. I was thinking for the tangential pressure, we could cut the sphere in 2 halves, compute how much they attract each other, and divide that by the contact area of the cutting ring. However, the standard gravitation force formula only works for spherical objects, and here we have half spheres, and I'm absolutely too lazy to evaluate the integrals over all points in those halves. Forgot the rings there. For the radial pressure, I have not even a slight concept of how to do that. The thing is, on the outer side of the wall there is no radial pressure because there is no weight on top. On the inner side of the wall there is no radial pressure because there is no gravity inside a hollow sphere. It just compensates itself. But does it peak in the middle of the shell, or is it zero all the way through the crust because the individual onion slices of the shell don't put any pressure on each other because they are stable by themselves? No clue. Do I feel like running a finite element analysis? Absolutely not. I will just declare that the ferrok that we are using can withstand any pressure we put on it. Oh, and it's also absolutely stiff. If there is even the slightest elastic deformation, the sphere will shrink millions or billions of kilometers, which is still just a teeny tiny fraction of its radius, and thus the surface is no longer close to the event horizon. But on the other hand, as before, if we just start building and stop when the event horizon is where we want it, that problem would also be solved. Alright, let's finally get to the Einstein part. So I was asking myself, what would happen here? I heard about what happens as you approach the event horizon of a black hole. From an outside perspective, you become slower, redder, and torn aparter from the gravitational tidal forces, meaning the parts of you that are closer to the hole experience way more gravity, so you get ripped apart. The actual scientific term for which is actually spaghettification. But apart from that, they also say that mathematically an observer crossing the event horizon doesn't even notice it. So could our observer enter the event horizon of Lupa, where there is friendly Earth-like gravity everywhere, watch the universe age to infinity in the blink of an eye, safely land on the surface, and then solve Sudokus and her Rubik's Cube forever? What happens if she tries to put her hand out of the event horizon? Does it just go through and reach into the aftermath of foreverness of our universe? Is the event horizon a solid wall? Does the simulation we all live in crash? Does her hand fold in on itself? This is the point where I was when I started making this video. And of course then I did some investigation so I don't look like an idiot in front of you guys. And here is my take on what's going to happen. So the thing with the event horizon is this. An event can only influence its surroundings with the speed of light, because information cannot travel faster than this. So you can think of the influence region of an event like a cone in space-time, the so-called light cone. Only things from within the cone before the event can influence the event, and only things within the cone after the event can be influenced by the event. However, in the presence of a mass, this cone gets distorted. And in the presence of a lot of mass, it gets distorted so far that a line that is, let's call it parallel to time, so it stays in its place, is no longer in the cone. So as you approach a heavy mass, the space-time gets more and more distorted. And the border surface where the parallel line is just within this possible cone is the event horizon. Anything further in can only move even further in, and not because something tugs on its feet, but because of the way space-time is shaped itself. Are you kidding me? Just like you can only move forward in time in normal space, you can only move inward inside a black hole. It might sound weird and unimaginable, but then again, being naked is also frowned upon everywhere in the universe except in the sauna, where it's just the normal state. So, what does it mean for Lupa? I am pretty sure that it can't even be constructed. But I'm still curious at which point things start to get weird and in what way. The thing is, it's not like they are starting to construct the planet layer by layer and the black sphere is growing on the inside. There is no gravity on the inside. But what then? You have a giant sphere with nothing happening except everyone walking on it aging very slowly, and then you add one more atom to it and suddenly there is enough mass inside a small enough radius and boom, you have the thing collapsing into a black hole? That seems weird as well. Ah, wait. So, yeah, I don't know. I'm curious what you guys think. Curious, but not in a desperate, please comment on my video kind of way. So feel free to not think about it. One last thing. All the calculations for this video involved absolutely unimaginable numbers, but I still wanted to get them spot on. I did them in Python because it's nice. I used SymPy's symbolic solvers even for the simplest equations, Pint, which is capable of calculating with physical units, and I used MP-Math for arbitrary precision. And those three modules, which were not designed to know about each other, just worked together like a charm. It required some hacking, but it was way easier than I expected. I will do all my engineering calculations like this from now on. You can find a link to my spreadsheet in the description. Well, alright, that's it. Thanks for watching. Stay hydrated.